At 2:17 in the morning, the nuclear power station appeared almost motionless. Beyond the security fences, the reactor buildings stood beneath a moonless sky, massive and silent, their concrete walls pale under rows of cold white lights. Steam drifted from the cooling towers and disappeared into the darkness. From a distance, the station looked less like a machine than a sleeping city. But nothing inside it was asleep. Deep beneath the concrete, water moved through sealed pipes under immense pressure. Pumps turned without pause. Sensors measured temperature, vibration, flow, pressure, radiation, and electrical output thousands of times every second. Control systems compared each number against limits written by engineers decades earlier. Behind reinforced doors, operators watched illuminated panels where a single changing digit could mean nothing, or the beginning of something that could not be ignored. The public often imagined that radiation was the greatest danger inside a nuclear power plant. It was invisible, mysterious, and powerful enough to inspire fear even when safely contained. Yet the workers understood a different truth. The greatest danger was not always radiation. Sometimes it was routine. Routine made alarms seem familiar. Routine made a small vibration feel harmless. Routine whispered that a procedure had been completed hundreds of times before and would be completed the same way again. In a facility where every critical system had a backup, and every backup often had another backup, confidence could slowly become more dangerous than fear. That night, the reactor was operating at full power. Inside the core, uranium atoms were splitting in a controlled chain reaction, releasing heat without flame. That heat transferred into water circulating through the reactor system. The water carried its energy toward steam generators, where a second water circuit turned into steam. The steam rushed toward turbines, spinning enormous metal blades connected to an electrical generator. The generator produced enough electricity to supply an entire region. To the cities beyond the horizon, the station was invisible. Streetlights glowed, elevators moved, refrigerators cooled food. Hospital machines continued working. Millions of people used the power without thinking about the building in the darkness or the operators watching the panels. Civilization depended on systems it rarely noticed. In the main control room, the night shift had settled into its rhythm. The senior reactor operator sat before a wide console filled with screens, switches, and status indicators. Two additional operators monitored turbine performance, cooling systems, electrical distribution, and the condition of emergency equipment. Their work was not dramatic. Most nights consisted of reading instruments, confirming automated actions, recording values, and repeating checks that had already been performed by the previous shift. The room was quiet enough that the ventilation system could be heard. Every operator knew that boredom was part of the job. A nuclear station was safest when nothing unexpected happened. No sudden changes, no heroic decisions, no improvisation. The ideal shift ended exactly as it began, with every system stable and every procedure followed. At 2:23, a small indication appeared on one of the monitoring screens. The vibration level of a reactor coolant pump had increased, not enough to trigger an automatic shutdown, not enough to sound an alarm across the room. It was simply higher than it had been an hour earlier. The operator responsible for the system leaned closer to the display. The pump was one of the most important machines in the station. Its purpose was simple: keep coolant moving through the reactor. But its simplicity was deceptive. It operated under extreme temperature and pressure, and it was expected to run continuously for long periods without interruption. A reactor did not stop producing heat the instant the chain reaction ended. Even after shutdown, radioactive decay continued releasing residual heat. The amount decreased over time, but cooling remained essential. This meant the station depended not only on controlling the reaction, but on controlling what remained after the reaction had stopped. The operator opened the vibration trend. The increase was slow. For several minutes, he watched the line rise almost imperceptibly across the screen. It could have been sensor noise. It could have been a temporary imbalance. It could have been caused by a minor change in temperature. The machine was still within its operating limit. That fact made the decision more difficult. An alarm told a worker what to do. A limit created certainty. But a number approaching a limit demanded judgment. Acting too early could shut down a reactor unnecessarily, costing time, power, and money. Acting too late could allow a manageable problem to become something larger. The operator informed the UASOG. At 2:46, the vibration increased again. This time, the rise was faster. A warning alarm appeared. The calm atmosphere in the control room changed, but it did not become chaotic. One operator acknowledged the alarm. Another read the relevant procedure aloud. The supervisor assigned specific responsibilities. Each action was repeated back to prevent misunderstanding. In ordinary life, repeating an instruction could seem unnecessary. Inside a nuclear control room, repetition was protection. The supervisor made the decision to reduce reactor power. Control rods began moving into the core in carefully measured steps. The rods absorbed neutrons, slowing the chain reaction. Thermal output decreased. Steam production fell. The turbine responded as electrical generation was gradually reduced. Across the grid, other power stations compensated automatically. The cities noticed nothing. At the pump, the technicians continued monitoring. The sound had changed. It was subtle, but experienced workers heard machines differently. To an untrained visitor, the room would have sounded exactly as it had minutes earlier. To the technicians, a repeating low-frequency pulse had appeared beneath the normal mechanical noise. One of them inspected the external bearing housing with a thermal camera. A warm area was developing. The temperature had not yet crossed the limit, but it was rising. The supervisor now had two independent signs: increasing vibration and increasing temperature. At 2:54, he ordered the affected coolant pump stopped. The operator placed his hand on the control. Before pressing it, he stated the action. The second operator verified the correct pump. The supervisor confirmed. Only then was the command given. The motor disconnected from power. The pump began slowing. Indicators changed across the panel. Coolant flow in the affected loop decreased. Automatic control systems responded by adjusting other equipment. Reactor power continued falling toward a safer level. For several seconds, every person in the room watched the same set of numbers. The remaining pumps carried the required flow. Core temperature remained controlled. Pressure remained stable. No emergency system activated. The station was safe. But the event wasn't over. A stopped pump inside a nuclear plant did not become irrelevant, simply because the reactor remained stable. It had failed for a reason, and that reason had to be understood. The technicians waited until the equipment had fully stopped and conditions were confirmed safe. Then they approached for a closer inspection. Near the lower section of the pump assembly, they found a small amount of leaked water. It was not reactor coolant escaping into the building in a dangerous release. The leak was associated with a supporting seal system designed to control pressure around the pump shaft. Even so, it was a critical clue. A seal had begun degrading. As its performance changed, the shaft behavior had changed with it. That change created vibration. The vibration increased mechanical stress. The stress generated heat. Left uncorrected, the process could have damaged the pump more severely. The failure had not arrived suddenly. It had grown in silence. The first sign had been a number slightly higher than normal. At 3:20, the reactor was brought to a controlled shutdown. The turbine slowed. Electrical production fell to zero. Control rods entered fully. The chain reaction stopped, yet the plant remained alive. Cooling pumps continued circulating water. Electrical systems remained energized. Operators continued watching temperature and pressure. The reactor still produced decay heat, and that heat still had to be removed. This was one of the least understood facts about nuclear power. Shutting down the reactor did not end the responsibility. It changed the responsibility. The plant moved from producing power to protecting the fuel while the remaining heat declined. The process required hours, then days, of controlled cooling. The machinery that mattered most after shutdown was often not the machinery that had produced electricity, but the quieter systems that carried heat away. At 4:05, engineers arrived to review the data. They examined the vibration trends, seal system pressure, maintenance records, and previous inspection reports. No one was permitted to decide that the problem was obvious without evidence. Assumptions were treated as hazards. The pump would remain unavailable until inspections confirmed the condition of its bearings, shaft, seals, and supporting systems. The reactor would remain shut down until the plant could demonstrate that safe operation had been restored. Outside, the cooling towers continued releasing steam into the night. To anyone driving on a distant road, nothing appeared unusual. There was no explosion, no visible emergency, no crowd running from the building. There had only been a small deviation noticed by a